This is also derived in your book, but sometimes when you get to these calculus parts of physics, it's sometimes hard to follow. So hopefully I'll be able to help you understand these derivations. These are the calculus-based things that that make calculus-based physics what it is. So these are the more difficult parts of this. So what we're looking for is we're looking for the electric field at this point P due to this ring being charged. So there's an excess charge one way or the other, either positively or negatively charged. It's conducting, so it is the charges are distributed uniformly around this. So we have Coulomb's law. Well, actually, we're trying to find the electric field at this point, and then once you have the electric field, and if you have a charge here, you can calculate the force. So if you remember, the electric field is equal to Coulomb's constant times the charge divided by r squared. So as we always do in calculus, we take an infinitesimal element and we look at the charge of this small element, and then we determine the electric field due to this little charge, and then we integrate around the entire circle to get the total electric field. So because this is has an infinitesimal size to it, it's also going to have an infinitesimal charge. So we use the differential form of the definition of the electric field. So you're going to have dE, which is a differential of the amount of the electric field. K is a constant, and you're going to have dQ here. So it's a small charge. The radius for this particular charge is fixed. So these two are fixed. So when you take the derivative, you get these two terms. And it turns out they use the other form where instead of using K, they use 1 over 4 pi epsilon 0. So we get, for K, we put in 1 over 4 times pi times epsilon 0, and then you get dQ divided by r squared. So the first thing that we do is we have to figure out this little dQ is, so that we can substitute in for what dE is in terms of the charge. So what you're going to have is you're going to have a total amount of charge for the ring. So that's the total charge on the ring. So however many excess electrons or deficit of electrons. So the differential, the amount on that little area here is going to be the total amount. And you take the length of this little element, so this dl is the arc length, divided by the total length. The total length is 2 pi times the radius of the ring, which is a. And what we're going to do is we are going to call this part lambda for the calculations. So we're going to say that lambda is Q, the total charge, divided by 2 pi a. These are all constant values for the particular situation. So then you end up with lambda times dl. So dq is lambda times dl. This is the charge per unit length. So now we can what we can do is, so what we're looking for is this dq. Actually, I should have used a small q. I used a big q. So we can make the substitution into there, and we get that the small amount of electric field, and this electric field is going to be pushing in this direction. So dE, the vector, well, actually the vector is going to, we're going to have a direction, but we'll deal with that in a second. The magnitude is just going to be equal to K times dQ, which is lambda dl. So we're taking this equation. For dQ, we're putting in lambda dl, and then we're dividing by r squared. Oh, that's right. We were going to use 1 over 4 pi epsilon 0 instead for k. Okay, so now what we're going to do is we're going to do two things. We're going to look at this force. Let's say you have a little dl down here that's at the opposite end. And it's going to have the same length. So if I take this vector like this, it's going to be the same as this one here, except it's going to be pointing up. And it's going to have an x component and a y component. So there's the x component, and there's the y component. Well, this one is going upward, this one's going downward, so those cancel. The components parallel to this axis cancel out. So the only component that actually comes out of integrating around this whole thing is the axial component. You know, we have a little element here which is balanced by this little element there. So these all cancel out as you go around. It's always something. It's a round ring. So the total electric field is going to be the sum of all the x components of this electric field. So here we have a right triangle, and this is the angle theta. So this angle theta here is also equal to this angle theta there. And if we drew this, you know, this is the opposite side, the adjacent side. So the x component is going to be this hypotenuse times the cosine of theta, and I'll give you that bit. So the total electric field is just going to be the x component because the y components cancel out. And to get that, we add up all the differential amounts all the way around the circle. And because of this geometric relationship, the x component is just equal to the cosine of theta times dE. And then we have the dE, the differential of the electric field, which is this length here, is equal to 1 over 4 pi epsilon 0 lambda dl over r squared. Now, what we want to do is we're going to we want this as a function of x and not as a function of r. So we need to write this little thing 1 over r squared as a function of x. So how do we do that? Well, let's first take out what we can. This is a constant. It's defined as the charge per unit, or the charge per unit length, and all these are constants. So we get lambda over 4 pi epsilon 0, the integral of dl over r squared cosine theta. So let's both of these we can put in terms of x. So it's just a matter of looking at this triangle. So let's add a page and just draw this thing out. So you have, let's go back here, make sure we do this right. So let's, this distance is the r distance, this is the x distance, this is the a distance. So we got this right triangle, which is not quite a right triangle, so I need to bring that over. There we go. So this is theta, this is r, this is a, this is x. So the cosine of theta, in terms of these distances, cosine is x over r, adjacent over hypotenuse. We also know that r is equal to the square root of a squared plus x squared. So r squared is a squared plus x squared. Okay, so if we look at cosine of theta over r squared, we had a page here. Cosine of theta divided by r squared. Cosine of theta is x over r divided by r squared. So we get x over r cubed. So x is, we just leave that the same because that's what we're trying to get this r in terms of x and a. So what we have is r, which is the square root of a squared plus x squared, and when we cube it, and so the ratio of the cosine of theta over r squared in terms of x and a is x divided by a squared plus x squared to the 3/2 power, because you've got cubed to the 1. 3 times a half is 3/2. Okay, so we'll go back and do that now. So we can bring that out, and so what we'll have is lambda over 4 pi epsilon 0 times x over x squared plus a squared to the 3/2 power, and then we integrate dl. And we integrate that from theta equals 0, well, from x equals 0 to the total circumference, which is 2 pi a. So we'll get lambda over 4 pi epsilon 0 times x over x squared plus a squared to the 3/2 power. And so when you integrate dl, you get L evaluated between 0 and 2 pi a. So when you plug in L equals 0, you get 0, so we just get the upper limit. So I'm going to move that up front, 2 pi. So this goes in for L, but then I'm going to move it out front. So you get 2a times lambda times x, all divided by 4 pi epsilon 0 times x squared plus a squared to the 3/2 power. So that is the value of the electric field in the x direction. And it turns out that if we go back here, when we were doing this calculation, I think, where was it? I think it was back here. Q is equal to 2 pi a times lambda. So I have 2 pi a times lambda, so this part right here is Q. So the final answer in terms of the total charge on the ring is going to be, and this is what's in the book, so I'll write it in their form, it's just things moved around a little bit. So you get 1 over 4 pi epsilon 0, you get Q, the total charge on the ring, times the distance along the axis from the center of the ring, divided by x squared plus a squared to the 3/2 power. So let's just kind of review what we did there. I might have to jump around a little bit. We wanted to find the electric field at any point, any distance x from the center of the ring. The distance from the center of the ring to the point of interest is x. The distance from the center of the ring to the outside of the ring is a, which is the radius of the ring. And the distance from the actual ring piece to the point P is r. A squared plus x squared equals r squared. So we looked at the differential form of the electric field. So instead of having E, we had dE. Instead of having Q, we had dQ. The differential charge on part of the ring is equal to its charge per unit length, which is this term, times the length, the little dl length around the ring. We called Q over 2 pi a lambda, which is the charge per unit length of the ring. So dq is equal to this charge per unit length times dl. So we took that and we plugged that into here, and we also rewrote it in this form. So k is also equal to 1 over 4 pi epsilon 0. So then we go back to the beginning here, and we ended up with this, the differential contribution to the electric field at this point is equal to 1 over 4 pi epsilon 0 lambda, the charge per unit length times dl, this little differential length divided by the distance from here to that point, the straight line distance. So then we integrated it, and all these are constants for a given value of x and for a given charge on the ring. So the only thing we actually had to end up integrating was dl. We wanted to rewrite okay, and then we also made the observation that the perpendicular components of this dE were going to cancel out, because you always had one going this way from the top and one going this way from the bottom, but the x components all go in the same direction, so they add up. So we said that the total electric field on this point, at this point P, is the x component of the electric field, since the y component is 0. So we integrate the differential amounts of the x component of the electric field, which is the actual electric field times the cosine of theta, just from this triangle. So we plug all that stuff in there, and we end up with this, we end up being able to substitute cosine of theta over r squared. We could put that in terms of x. That was what we did over there. Was here. Let me go. We had 2 pages. Cosine of theta is adjacent over hypotenuse. The denominator in the term that we're trying to determine is r squared. So when you simplify this, you get x over r cubed. R is the square root of a squared plus x squared. Then you cube it, so you get to the 3/2 power. So we substitute that into here for cosine of theta over r squared. And because it's a constant, we can bring that outside. We could have brought it outside. We didn't have to do that inside the integral. They're constants. So the only thing we had to integrate was dl. So if you integrate dl, you get L. And we go from the beginning of the circle to the end of the circle. 2 pi a is the circumference. We plug that in for L. You get 2 pi AL. 2 pi a times lambda times x over all this stuff. You rearrange them. You rewrite 2 pi a lambda as the total charge on the ring.